All right, well, we're here today at the National Center for Atmospheric Research in the Atmospheric Chemistry Division, and I've got a great privilege and opportunity to work with one of the physical chemists here to look at a particular atmospheric chemistry that's very relevant to us here in Colorado, especially Denver, and that's Denver's brown cloud. So as an introduction to our kinetics, I wanted to give a little background on the brown cloud and how a physical chemist would use kinetics to measure and determine some of the factors that affect this reaction. So, first of all, we need to understand why the brown cloud forms. And the key to the brown cloud in Denver is what we call an inversion, a temperature inversion. I'll just put T out front here. So, in normal conditions, if this is the ground level, you have the sun heating up the ground and warming the ground, which warms the air above it. And you have cooler air up above that, because we know that as you go higher in altitude in general, it gets cooler. So warm air expands and rises, and so you get normally what we call vertical mixing, which keeps the air pretty well mixed and pollutants pretty well mixed, and so there's no buildup. Now, in the winters, in Denver in particular, we can get the opposite phenomenon, which we call an inversion. And I'm drawing my ground level like this because Denver actually sits in a bit of a valley. So during the winter, what happens is we get cold air at the ground level, and we actually kind of get a cap of warm air up above it. And so the sunlight that hits the ground is not sufficient to warm the ground or sufficient to warm the air, and so we don't get vertical mixing, and we call this an inversion. And as a result, you can imagine that pollution gets trapped in that cold air layer, and ultimately, I'm going to use a different color here, we get the brown cloud. So that's kind of a crude overview of how the brown cloud is produced, and that it's a seasonal factor for the most part. So what specifically is in the brown cloud? Well, there are a number of things. First of all, we talk about BC, or black carbon. This is particulates. This is what you and I know basically as soot. From factories, we also have fly ash, which is particulate, which is exactly what it sounds. It's ash from combustion processes that has flown up into the air. A lot of factories will capture this to prevent it from going into the air, but some of it occurs. We also get dust from soil that just naturally blows up into the air, and we get it from especially in the winter, salt and sand mixtures that get ground up and kicked up into the air. So these are all components of our brown cloud. But last and certainly not least are nitrogen compounds, in particular nitrogen dioxide, NO2. And we're going to look today to see how NO2 is produced and how it contributes to this brown cloud, and why it's a concern for you and me in the winter, and how this generates what we know as pollution alert days or our red alert days or whatever they're calling them now. So at this time I'd like to introduce our physical chemist here that is going to, we have the opportunity to visit his lab today and see how he generates this data and derives kinetics. He derives rate constants for different sorts of reactions. This is Dr. Jeff Tyndall. Mm-hmm. Jeff, thanks for working with us today.
Thank you. Yeah, it's a pleasure. Yeah, and so we're going to go into the lab shortly and do a little demonstration and try to see some NO2 being formed, make a little brown cloud ourselves. And nitrogen oxides are emitted by cars and factories, mostly as NO, nitric oxide, and then the NO gets converted pretty rapidly to NO2, which is, say, a brown color. And so we're going to use some of the properties of these molecules to detect them and to try and measure the rate that the NO2 is being formed. So we'll take a look at that shortly. And NO2 itself is actually really central to forming ozone in the atmosphere, and that's one of the other major pollutants that isn't colored, so ozone gets formed and it kind of stings your eyes and inhibits crop growth, so it's really important to understand ozone chemistry. It's a big part of what we do. But today we're going to look at this conversion of NO by oxygen to make NO2, which is then part of the brown cloud and a precursor for ozone. So,
great.
Okay,
let's go on into the lab.